All right, today we're going to pull back the curtain on a really cool magic trick, one that's hidden deep inside the world of computer programming. Now, it's a technique that kind of seems to defy logic, but as you'll see, it's all built on a beautifully simple idea.
Okay, so let's set the stage for our first illusion. It all starts with a classic programming puzzle. You know, the kind that really stumps a lot of people the first time they hear it.
I want you to really think about this for a second. Let's say you have a variable a that's holding the number 5, and b is holding 10. How in the world do you get a to hold 10 and b to hold 5 without creating a third temporary variable to park one of the values in? It seems impossible, right?
Well, believe it or not, this is the answer. Just 3 kind of cryptic-looking lines of code. No temporary variables anywhere. And this little sequence, it perfectly swaps the numbers every single time. The big question is, how on earth does that even work?
To understand the secret behind this little piece of magic, we need to meet the star of the show, a simple but incredibly powerful tool called the XOR operator.
You see that little caret symbol, the V? That's XOR, and it stands for exclusive OR. Now, the key to its power is that it doesn't see numbers the way we do. It's a bitwise operator. That means it goes all the way down to the binary level, the ones and zeros, and compares two numbers bit by individual bit.
Let's see how that works. If you take two numbers, say 5 and 3, XOR first converts them into their binary form. Then, as you can see here, it lines them up and just compares each column of bits one at a time.
And the rule for that comparison is so simple. This is the only thing you have to remember. If the two bits it's looking at are different, a 1 and a 0, the result for that column is a 1. If the bits are the same, both are zeros or both are ones, then the result is 0. That's it.
This right here is called a truth table, and it just shows that single rule perfectly. 0 and 0, they're the same, so you get 0. 1 and 1, also the same, so you get 0. But anytime they're different, like 0 and 1 or 1 and 0, bam, you get a 1. That's the entire logic, right there on one screen. Now, just like any good magic trick, XOR's power comes from a few simple, unbreakable rules. And once you know these rules, you can perform the magic yourself. First up, we have the identity property. If you XOR any number with 0, you just get that original number right back. Absolutely nothing changes. It's kind of like adding 0 in regular math. This is a crucial foundation for what's coming next. And here's the real showstopper, the cancellation property. If you XOR any number with itself, the result is always 0. This is because at the bit level, every single bit is being compared with an identical copy of itself, so the result is just a long string of zeros. Finally, XOR is also commutative and associative. Now, that's just a fancy way of saying the order doesn't matter. You can swap numbers around, you can regroup them in a big long chain, and the final result will be exactly the same. This flexibility is what makes our tricks possible. Okay, so let's go back to that swap trick with our new rules. In line 1, A becomes this new mashup of the bit patterns from both A and B. Now for line 2, we XOR this new A with the original B. So that's really original A, XOR original B, XOR original B. And thanks to our cancellation property, the two B's just cancel each other out. They become 0, leaving just the original A. So B now holds what A used to. And finally, in line 3, we take that combined pattern still in A and XOR it with our new B. But wait, our new B is the original A, so the two A's cancel out, leaving only the original B. And just like that, the swap is complete. No tricks, just pure logic. So that was a pretty neat trick. But now, for the grand finale, let's see how those same simple rules can solve a problem that seems way more complex and do it with incredible style.
So here's the puzzle. I give you a list of numbers. Every single number in that list shows up exactly twice, except for one lonely number. Your job is to find that unique number and do it efficiently. Let's use this list as an example. We've got a 4, a 1, a 2, then another 1, and another 2. Now you and I can just look at that and see, oh yeah, 4 is the odd one out. Easy. But how can a computer figure that out without having to, use up a ton of memory or time? The secret, once again, is our amazing cancellation property. Remember, any number XORed with itself is 0. Keep that right at the front of your mind. So what if we just take every single number in that list and XOR them all together in one big chain?
Since we know the order doesn't matter, we can just imagine grouping the matching pairs together.
And now look what happens. It's beautiful. The 1 XOR 1 becomes 0, the 2 XOR 2 becomes 0, every single pair in the list cancels itself out and just vanishes into a 0. So what are we left with? Our lone survivor, the number 4, XORed with a bunch of zeros. And because of the identity property, we know that just leaves us with 4. By XORing the entire list, we instantly find the one unique number. How cool is that?
This might still seem like just another clever puzzle, but this is exactly where the magic trick transforms into a seriously powerful professional technique.
And here's why this really matters in the real world. Most other ways you might solve this are actually pretty inefficient. You'd probably need to use extra memory to keep account of each number. Or you'd have to sort the list first, which is slow. The XOR method, though, it's brilliant because it's insanely efficient. It uses no extra memory, and it only has to go through the list one single time.
So what starts out as a fun little brain teaser is actually a foundational concept used in really complex algorithms, in data transmission for checking errors, and even in some forms of cryptography. It's just a perfect example of how powerful these simple bit-level operations can be.
And that leaves us with a final thought. We've just seen how thinking at the most fundamental level, the level of individual ones and zeros, can solve problems that seem incredibly tricky on the surface. It really makes you wonder, what other impossible problems are out there, just waiting for a solution as simple and as elegant as XOR?